Here with me today are several of the key team members responsible for the development of our latest calorimetric system that has brought about the calibration process for these next-gen sensors. Tim Holt is the senior technologist with the Test and Measurement Group. He has over 35 years of experience in the design and development of RF power measurement products for both commercial and military applications. Jacob Perchlick is our chief metrologist, and he is part of the development team responsible for the continuous improvement of bird measurement standards, specializing in RF power measurements. Jeff Kliss is a software engineer with the Test and Measurements Group and has served a lead role in the design and development of the electrical software systems driving Bird's latest gen calorimetric system. Before we get started, I'd like to take a quick poll to get a rough idea of how familiar you all are with RF power calibration methods. Calorimetry, terminating power sensor, and Type 4 bridge are some of the most popular we have seen in the field, but if you use another method, please feel free to share with us by submitting your comments through the questions interface. You may also select more than one option for the poll if it applies to you. So Tim, while we're waiting for everyone to submit their answers, do you want to go ahead and start giving us a breakdown of some of the different options?
Sure. Clearly, there are several methods, as you outlined here, that can be used for measuring, for precision measurement of radio frequency power. And one of the first ones, one of the most popular ones actually, is the use of a terminating power sensor with an attenuator or a directional coupler. And the reason you use the directional coupler or the attenuator is that these terminating power sensors are typically very, very low power measurement devices, typically 100 milliwatts or less. And so they need some type of attenuation in order to bring that high power level down to a reasonable power level that can be measured by the sensor. These instruments are typically very broadband and also have a very high dynamic range as well, and that can aid the measurement or can be detrimental to the measurement as well. The next type of system that's used for precision measurements is the NBS Type 4 bridge, or the NIST Type 4 bridge, that was originally pioneered by Weinschel Engineering back in the 1960s. And I'll ask Jacob Perchlick to say a few words about that thing because he uses them every day.
Oh, thanks, Tim. So the Type 4 bridge is use a DC substitution really to measure RF power. Because RF power is a difficult thing to measure directly, as we'll go into more detail throughout this presentation, we often use other ways of measuring power and translate that into our RF power measurement. Like the terminating power sensor, the Type 4 bridge is a low power measuring system. So if you want to measure high power with a terminating thermistor mount and a Type 4 bridge type power meter, you're going to again need an attenuator or a directional coupler like the terminating power sensor. And
all right. Hey Jacob, let me just put the conversation on hold just a minute. It looks like we've got the majority of our audience has voted. I just want to take a quick second to review these results with everybody. Okay, so it looks like most of the folks here are familiar with the calibration methods using directional coupler or with an attenuator. So I do want to take a moment to address the popularity of these other methods versus calorimetry, but I also would like to have Tim and Jacob and bring Jeff into the discussion here to finish talking about these three different types of methods. So Jacob, if you want to continue your discussion of the Type 4 bridge, that'd be great.
Right, so NIST originally developed this, which is a CN40 thermistor mount. So what happens is you put RF power into this little device, it gets dissipated in the load here, and then using the Type 4 bridge, you can measure basically the power difference between a DC source or internal DC voltage measurement before RF power is applied and then after RF power is applied. And in doing so, you can then indirectly back out the RF power that was applied to this system. This is a very indirect approach like all other RF power measurements, and maybe Jeff can now speak to a little bit of the calorimetry and how that's an indirect approach to RF power measurements.
Sure, thanks Jacob. Yeah, so calorimeters work on the principle of conservation of energy. They're considered to be the most accurate way of measuring RF power. And basically you're trying to convert all of your RF power or electrical energy into thermal energy and then measure the thermal energy either as the heat change in the load itself or a heat change in the coolant that's used to cool the RF load, and then measure that thermal change, and the RF power that's being dissipated is proportional to your temperature change. And the more accurately you can measure the power being dissipated. And fortunately, it can be mostly independent of the frequency of the RF power that you're trying to measure because of the principle of conservation of energy. But yeah, so that's basically how calorimeters work.
All right,
Yeah,
thank you, Jeff.
just one more word on calorimeters. They're kind of the last word when it comes to RF power, precision RF power measurements, because NIST actually uses calorimetry as the basis for all RF power measurement standards that are established here in the United States and around the world as well.
Yeah, to Tim's point, even this thermistor mount here is hooked up to a microcalorimeter in order to be calibrated. So in order to get a power measurement from this device, it has to go through a microcalorimeter. And as Tim said, this is how they define the watt. Without that, we would not be able to measure power accurately and repeatable over time. And because of this, there's often the problem of how do you measure an accurate power measurement? And that really comes back to what's your most traceable path? What is the simplest traceable path back to the ST standards? And if we compare calorimetry to a terminating power sensor or this thermistor mount, what you'll see here is on your left, you'll see the radio frequency calorimetry that we use at Bird traces its power measurement back through an AC power meter, which then goes through AC and voltage standards of working standard groups, and then that traces back to the national standards. However, if you're looking at with something like a Type 4 bridge power meter at high power or a terminating power sensor at high power, you actually have a dual path back to the national standards, which was going to increase the uncertainty of your measurement and the long-term reproducibility of your process. So you have a working standard. It has to go through the power measurement part, which is a low power measurement, like Tim and we had mentioned. Your maximum wattage you're getting from a terminating power sensor is 200 milliwatts. For a thermistor mount, you're maybe getting 10 milliwatts. So you're going to need a directional coupler and to sample some of that main RF power line in order to get a power measurement, which means that you actually have two different traceability paths through the attenuator or coupler and through the power sensing measurement back to the national standard to get your definition of a watt. And as you can imagine, this adds a lot of complexity into your uncertainty budget and adds a lot of complexity and increase in uncertainty of every measurement that you make.
Yeah, Jacob mentioned that magic word, uncertainty budgets, because measurements, we can all make measurements and we can claim to make measurements, but it all comes down to what we can prove. And the uncertainty budget provides a means to do that. As Jacob mentioned, the uncertainty budget for the system on the right, involving either a terminating power sensor and a directional coupler or an attenuator, is necessarily more complex for lots of reasons.
Thank you, Tim. Jeff, do you have any points to add to the conversation here?
I would just say that at Bird, we use all of these different standards for calibrating our instruments. They all have their place and their purpose. But if you want to make the most accurate power measurements, you need to go back to calorimetry, and that's why we're focusing on that today.
I would like to add a little to Jeff's point, and that is some of these measurements are faster than others. Calorimetry here at Bird takes about 10 minutes. A Type 4 bridge power meter setup with your thermistor mount, depending how particular you are, can be about 5 seconds to maybe a minute. Your terminating power sensor can make these measurements on fractions of a second. So there is benefits to using one technique over the other in your specific application, but if accuracy above all else and long-term reproducibility is what you're interested in, calorimetry has to be where you go.
Those are great points, Jacob. Are there any other comments on the comparison to calorimetry for directional coupler methods and Type 4 bridge that you guys would like to make before we move on to the next subject?
I'll just have one other comment, and that is that one of the key characteristics of calorimeters is that they measure heating power, and they measure the power of heat. And because of that, we're able to measure low frequency energy to a very high accuracy and use the AC power, low frequency AC energy, or actually DC energy to essentially calibrate the calorimeter at a much higher accuracy than you could in an RF system. So it's just one point. It's kind of one of the key points of calorimetry that makes it unique.
Okay, and as far as the traceability path, is that where the 0.5% sensor is able to really come alive, is due to the more narrow traceability path?
I'll let you take that one, Jacob.
Yeah, definitely. So because we control the standard and we control its very short traceability path, we can make longer term reproducible results with a narrower band of acceptance criteria. We can claim a lower uncertainty because we hold our standard here dear, and we have basically the watt defined here at Bird. And we have to go through the process of defining that, and we do that in a very particular manner. And we really have to use physics in order to get there. So in order to do this, you can't just say we're going to do this on a whim. We need the physical equations that govern calorimetry to be intact and understood in order to make these measurements.
Right.
Sure thing. So I guess this is a good time to bring the slide back up.
Just a few words about the mathematics.
Yes, right.
Yeah.
So, as Jeff previously stated, calorimetry works on the basic principles of conservation of energy. You have heat energy is equal to electrical energy, and because physics works, this is a true statement. And so what we do in calorimetry is you say that the rate and change of the heat energy, or the power, is equal to the specific heat of the material, so how much energy that material can absorb per degree, the flow rate of a flowing fluid through our load, because that's where actually all the heat's dissipated. So almost all RF power measurements, even your terminating power sensors, even your little Type 4 bridge thermistor mounts here, they all turn RF power into heat, because that's a lot easier measurement to make. And for the flow calorimetry that we do at Bird, you then take that power equation and you convert it and do it in this way and see that what's going to matter is specific heat of your material, the flow rate of your material going through your load, which is dissipating the electrical power, the density of the material that's flowing through, and the rate of change of the temperature, or the absolute change in the temperature. And Jeff can speak to a little bit, I think, of the intricacies of all of these things in our calorimetric system.
Yeah, so in order to get an accurate calorimeter, you have to be able to understand all the different parts of that equation. So you got to take the flow, you need an accurate flow sensor that can measure that, and then you need to be able to control the flow so it's consistent during a 10-minute possible measurement time. And the better that you can measure the different parts of that equation, the better accuracy you're going to get in the calorimeter. And that's what we've spent a lot of time doing on our calorimeter is collecting that data, selecting the right components, building custom components, custom parts and algorithms for controlling these things, and then combining it all in a system that works well together to produce the accurate results that we're working towards, which ultimately results in our 0.5% sensor that we've recently come out with.
So Jeff, to your point, I know there's a lot of complex system dynamics that are at play here. And even just looking at the equations, you can see we're really focused on a power level. Now, is the 0.5% accuracy, can we call that okay across the dynamic range of the 0.5% sensors?
I mean, Jacob could probably answer that question better than I can, but we usually quote 0.5% at the calibration frequency and power level, and then there is some wiggle room outside of that, but I'll let Jacob answer that one more.
Sure. Yeah, so actually for these 0.5% sensors, we've tested them across the dynamic range and across the frequency range, and they are 0.5% in those ranges at the cal points. So if you go away from the cal points, they're not necessarily be a 0.5% sensor, but at the calibration points and over the range of powers that they're quoted at, they are 0.5% sensor.
All right, thank you for the additional comments. So one thing I want to get a chance to talk about, especially as we're talking about, at a calibration point or over a dynamic range. So as we move into the, this advanced calorimetry that we are in right now and comparing to, previous generations, can we take a look at the legacy calorimeter versus the new calorimeter data that you had provided a slide for?
Oh yeah, absolutely. That's perfect time to do it, I think.
One comment before you go there, Jacob. Just wanted to say that so Bird's been making calorimeters for a long time, very long time, even long before my time, actually, if you can believe that. But the reason why Bird used calorimeters in days gone by is that calorimeters measure heating power, which is the true definition of the watt. The true definition of power is the power to produce some level of heat. And when complex waveforms in communications were first introduced, and specifically NTSC television waveforms that are complex include various modulation types. And Bird did not have a method for measuring the heating power of those types of waveforms, even though the Federal Communications Commission actually dictates that that transmitter power be held to a specific, plus or minus 5% kind of level. We needed to have some way, Bird needed to have some way to be sure that the power meters that we supplied to the industry were actually, in fact, meeting that criteria. So we used calorimetry first with mercury well type thermometers and a rotometer type flow meters that were used with tables that were used to actually calculate power values and compensate for various coolant physical characteristics and parameters. So anyway, but these instruments are calibrated at some point in time using a 60 hertz reference, and then that 60 hertz reference is then taken away, and that we rely on the inherent stability of the calorimeter system to maintain its calibration. So in order to meet the new challenges of 0.5% sensors, very, very accurate measurements and low variance, we needed to do things differently. And we're going to be talking about some of those things as we move through the rest of the presentation. But anyway, I know that it starts with what Jacob was about to talk about, the differences between traditional calorimeter systems and the calorimeter systems that we're bringing online now.
All right, thank you, Tim. Here I will bring the slide up here.
So for all of our power measurements, or our calorimetric measurements, we use a 60 hertz reference because it's actually easier to measure 60 hertz power with a multimeter effectively. If you have power meters that can measure these things to accuracies of like 0.0% at the power levels that we're concerned with, which is about 1700 watts. And because AC power is the same as RF power, there's no actual difference between the two. Anything that gets dissipated in the load gets turned into heat. We can reuse the separate measurement of the AC power with a power meter to basically verify our calorimetric system and see how well it's working at converting electrical power into heating power. And that's what we really have plotted here. So we have the green squares throughout this plot for the last 6 months are the legacy calorimetric system that Bird's had for about 25 years. And these are the basis for the 1% Bird product. The repeatability of this system, Tim has one. This is the calibration standard for that product. So for a 1% standard, a 1% unit, I guess, that you put into the field, 0.32% repeatability is good. I mean, you're a TOR of about 3. So your standard is not adding a lot of uncertainty into the measurement of your device. However, if you're talking about a 0.5% sensor, then 0.32% is almost half of your fraction of your uncertainty budget. And so what are you going to do? I mean, you're basically going to give sensors that vary by 0.32% from day to day, possibly. And that would not be good for a 0.5% sensor. For 1%, again, it's fine, but for 0.5%, you really need to beat down that long-term repeatability, reproducibility of the process. And so this new calorimetric system, which again, I should mention, unlike the old calorimetric system, integrates the reference standard, our AC standard, in real time, is able to beat down on these long-term reproducibility, repeatability of the old calorimetric system by at least a factor of 4. So here we have the long-term measurements for these two sources. Again, the black circles are the new calorimetric system, and the green squares are the old calorimetric system. And you can see, actually the red lines here are our adjustment criteria for that calorimetric system when we would adjust it if we notice it's outside of that. And the gray lines are, we would consider the specifications of this entire calorimetric system for the new system, not the old system, and at AC power levels. And you can see that the AC power measured by the calorimetric system in our new calorimeter is much improved over the measurement made by the legacy system. And that has held up for now almost 6 months. And it really gives us confidence to then calibrate things like our 0.5% sensor and be confident that we don't actually have to build a perfect measuring device that we put out in the field, and it has to stay that way for a long time, which is an unrealistic expectation, by removing that calibration uncertainty from those particular units. And I think Jeff might be the great person here to talk about what goes into this data. You know, what blood, sweat, and tears go into making something for a factor of 4 more repeatable than the previous system that we've been holding dear for about 25 years.
And Jeff, as you begin that conversation, let's also even consider, you know, for the folks out there that are, you know, looking into calorimetry for their own processes, you know, not only the types of challenges that we faced here, but also what kind of challenges might someone out there expect when they're trying to get into calorimetry to start?
Sure, yeah. If you want to take it to the next slide, I think that
Sure.
is a good place to start with this conversation. So like Jacob said, the biggest innovation that we made with our new calorimeter is integrating that reference standard into every measurement we take. And that's important because of what this graph shows right here. And this is the long-term stability of a delta T measurement. So when we're measuring power with a calorimeter, we measure the change in the heat, right? So the change in that temperature when we tried to hold the AC power source constant for this long period of time, and we measured that and maintained that constancy. I think on the left here, it says the variance of the AC source over this time period stayed within 0.02%, but the delta T measurement changed 0.26%, and 0.26% is too much. We can't accept that when we're trying to create a calorimeter that's repeatability is less than 0.1%. So integrating that reference standard is important because as the system adjusts or as it changes due to many different factors, the calorimeter continues to almost calibrate itself as it goes back to that reference standard. So that was probably the biggest innovation that we made in this system. But as other people try and use calorimeters, or as anybody tries to use a calorimeter, you have to understand that everything affects the accuracy in the measurements that a calorimeter is making. As the room temperature changes, as the humidity in the room changes, the fluid itself within the calorimeter changes. I mean, everything. You can't expect that it's all going to stay constant. Things are going to change around it, and all of that affects the accuracy of the measurement of the calorimeter, especially when you only calibrate the calorimeter infrequently. Like our legacy calorimeters are calibrated once a day, but the room temperature is going to adjust all day long, and you're only calibrated at the point that when that calorimeter was calibrated that day. And that's true for most calorimeters that are seen in the field, is they're calibrated once, and it's calibrated at whatever the dynamics were at that point in time. And as those things change, the accuracy of the calorimeter are going to change as well. So it's really important for us to create an environment where our calorimeter can work properly. So we have room controls for temperature and humidity, and we're measuring those things constantly. We're measuring our fluid composition and the fluid temperature. We're measuring our loads. We make our own loads here, so when we have problems, it's easy to go over to the loads department and get a new one. if I need a coupler or something to measure something, Tim can always throw one together for me. And so as a team, we're really good at controlling this process, but a lot goes into it, and you have to understand all those things. And it would be extremely difficult to make a calorimeter by yourself, or try and even operate one without acknowledging all these things that go into the measurement itself, and then accounting for them in your error budget, or however you're measuring your accuracy and repeatability.
Just let me make a comment, Jeff, to what you're saying there. One thing that really helped our cause as we were challenged with faced with a new challenge from the industry to produce a much more accurate measurement system, was the fact that, as we mentioned before, we've been making calorimeters for a very long time. So all of those variables that Jacob talked about and Jeff talked about in the calorimetric equation and in the way that you derive power in this way, we had a lot of familiarity with. So, so developing the instrumentation that was necessary to make those measurements, and then it came down to essentially characterizing the system and reducing variance, and then provide the best standard that we could provide for making that measurement. So, those were the essentials that we had to master as we move into this new calorimeter system. That's used again as the foundation for lots of the products that we'll be providing going forward. So again, it's experience and the willingness to cross disciplines on our technical staff. The fact that all of us all of us need to work together and provide use all of our knowledge in order to make this happen.
So to build on Tim's point of the accumulated knowledge here, I mean, if you look at the legacy calorimetric system, the repeatability was 0.32%. We found by using the new calorimetric system and the integration of the AC source that the repeatability of that, had we not accounted for the reference standard in real time, was 0.26%. Those numbers are suspiciously close to each other. So basically, it was a random uncertainty in our calorimetric system. Because we had the knowledge, we had the history to think about this issue for a longer period of time and kind of pick at it a bit more, we realized it's not actually a random uncertainty, it's a systematic uncertainty. It's a systematic uncertainty in how the system was operating. And we could improve on that because we've had the time, we've had the expertise to be able to pick out every little piece that we can of that equation and make things better. I mean, one thing I know Jeff and I have talked a lot about is air bubbles. It seems like a trivial thing, but air bubbles in your system will actually change the density of the material flowing through, which is going to change the delta T measurement. It's also going to change the specific heat because the amount of energy absorbed is different now because your air is not the same kind of heat accumulator that water is. And that kind of inconsistency will cause errors in your measurement if you can't account for it, or if you can't figure out ways to get them out of your system. So yeah, we've been able to look at all these little knobs and turn them, and because we've turned them in the way we have, that's why we've been able to really push down on our previous legacy system and be able to make this new system, which is a huge step forward in our capabilities.
Those are great points. I really like the discussion on the systematic versus the random error. Does anyone else have any comments to make on that? I think that's something that other folks might find particularly interesting for any type of test setup they might be implementing.
Well, just that as I mentioned before, it's all about what you can prove in terms of the measurement as well. So the construction of uncertainty budgets and error budgets for these instruments is critical, and the more that we can characterize every aspect of the system, the more we can correct for it. And just another comment, the tools that we have available to us today have helped us to do this. There's a lot better tools for doing this type of characterization and system characterization that we've never had tools like this available to us before. So that helped us very substantially along the way to making this happen.
So much better than what was available in the 90s.
Yeah, like nothing.
Yeah. Now, I do want to take a moment to, I have another interesting slide here talking about one of the challenges as far as like a failed component with the thermistor, I think, Jeff, that was one of the ones that you had put together. Do you mind if we take a moment to talk about this?
Yeah, let's do it.
Okay, let me bring up a slide here.
And I think that the purpose of that is to point to some of the challenges that we face along the way, and how to identify issues with the system.
Sure thing.
Yeah, so Jacob put together this slide. It wasn't me, but I'll talk about it first, and then he can I'll take as much credit as I can. So a big part of the calorimeter system is the stability of the temperature that you're trying to measure, right? So as you're applying power or switching power or things are changing, you want to make the power measurement when everything is as stable as possible. So on the graph on the left, it's showing different convergences over a length of time, or we do different runs. So that had all of those dots and clouds that represent several times the calorimeter tried to converge and make a power measurement. And it looks like the convergences on that graph are not converging to the point properly, or Jacob can say it better, but I'll let him say that better. But on the right, it's successfully converging and everything is very narrow. And I'll just point out quick that the scaling on this is really, really small. Like we're talking millidegrees C. So on the graph on the right, we're getting like better than 1 millidegree C at time of convergence. And those are the types of temperatures that we're measuring and trying to stabilize that in order to make these less than 0.1% power measurements. But on the left, what happened was a thermistor seal was broken, and it was the measurements weren't stable, and we were able to identify that because of its instability in this data collection set that we've got. So I'll let Jacob take it from there.
So I think one thing to point out is actually, even in this failure, this calorimetric system was still performing better than the legacy one. It was about 0.17%. So I mean, this is the level of detail we're talking about here. And yeah, so as Jeff's saying, those red bars, that's 1 millidegree C. So that's 1/1000th of a degree Celsius. I don't think you or I could detect that very easily. I don't know if Tim, looking at this, could have read that off the thermometer gauge.
Not a chance.
But Jeff has developed the programming around this, and has made this convergence criteria with modern computing a thing that this thing does every day. It does every day, all day, and because of that, we are able to push the boundaries of what how accurate a power measurement can be. And I mean, this is the things that we're caring about. We're caring about thousandths of a degree C in order to get this system where we want to, so we can build sensors that we can put in the field that are as accurate as possible.
Right.
Yeah, that's a great point, and I just want to kind of point that out to the audience that yeah, it's amazing how not only the challenges associated with calorimetry can be in characterizing the system when it's in a known good state, but also as components that are part of the system can experience difficulties like this with the thermistor example. And
maybe actually I'll describe this thermistor convergence. So basically, any kind of power measurement you make is going to take some time to converge. We talked about early in the presentation the terminating power standard, the type 4 bridge with a thermistor mount, and this calorimetric system. And because you're heating water, it takes a long time to get to equilibrium. It takes 5 or 6 minutes, and in our calorimetric system. It can maybe take longer or shorter depending on what kind of mass flow rates you are. This is the way we found it to be most stable. And because we're just waiting for stability, we have to wait a long time. You could probably take a shorter calorimetric measurement. I mean, you could, but the accuracy would be a lot worse. Your repeatability would go way down, and you would lose confidence in your ability to make measurements. It's like, again, like your type 4 bridge thermistor mount. That's why it takes several seconds. There's actually some circuitry in there that needs to equilibrate before it can make the measurement. And that's why that takes like 10 seconds. And your terminating power sensors, they are just snapshots because they are just trying to get the quickest measurement possible. Again, which is useful for some people, but it's not useful if you really want the most accurate long-term reproducible answer to what a watt is and what a power level is.
So I think this is a great time to lead into the idea of the long-term verification of the power sensors. So
That's kind of where the rubber meets the road, Steve.
Exactly,
Yeah.
exactly. So I've got a slide here that's showing some data as far as the long-term accuracy and long-term verification of the sensors. And so Jacob, maybe if you could break this down for us, and then we could get into a discussion of what does this mean for customers?
Okay, that's great. So what we have here is some power sensors that we've calibrated directly on our new calorimetric system. These are the 7036 series sensors, and we calibrate them, or 7030, yes, sorry, I apologize, 736 sensors that we've calibrated directly to the calorimetric system, or the 0.5% sensors, and that we then verify at subsequent states on the same calorimetric system. And in order for us to have a tight correlation between these two, minimal error, that is, the error with the power measured by the calorimetric system agrees with the power measurement made by the sensor itself, we need to have two things. We need to have a standard that's long-term reproducible, and we need a sensor that's able to hold that accuracy imparted on it by the calorimetric system for a long period of time. And so what you can see here is for 5 different sensors, we've done this test. Well, actually, we've done it for 15. I've only shown here 5 just for simplicity's sake. Not to give you too much scatter here, but or I should not say scatter. I should say too many points. But we can see is that a calibration was made in February. Oh, sorry, in March or January, and then we verified that in subsequent times and all the way till May. Now, and we can see that these power measurements made by the sensors agree with the calorimetric system to less than 0.1% in our tests. And what this means is most of the variation is actually probably due to the calorimetric standard itself, because we know the verification of long-term calorimetric standard is about 0.08%, and we're about that range for these standards. So what we have is a sensor that's able to hold its calibration point for a long period of time, and we have a standard that has a long-term reproducible result, and so we can verify this over a long time and just see how well this sensor can hold the accuracy that's been imparted onto it. So the red and gray bars here are acceptance and rejections criteria for these sensors, and you can see they're much wider than actually what we're seeing right now. So as we build this up and as we understand more about the system, we'll probably likely narrow these down a bit. And the level we're talking about is about 2.24%. I mean, this is the accuracy that we're talking about. This is at the cal point, at the calibrated frequencies. So at the cal level of 1700 watts, at the calibration points. This just happens to be a 1356 set of sensors, megahertz set of sensors. But you can see how well that accuracy just holds in time, and how we were able to prove it with our new calorimetric system and these sensors that we have.
Yeah, just a comment on that before we leave that topic, just to comment on your explanation there, Jacob. As when we embarked on developing this better standard, this better calorimetric standard a few years ago, one of the things that we knew and we were excited about was the fact that every single instrument that we calibrate on this system is going to be better, as a result. And even if we chose to use working standards that are calibrated to this calorimeter system and then use those on the production floor, the overall calibration of this, the overall accuracy and variance of those products are going to improve. And that's one of the reasons why we were so excited for this project. And again, it's been about 3 years in duration, been a lot of work, but certainly the results kind of speak for themselves in terms of the data that we collect. So that's just a point I wanted to make on that.
Sure. And Tim, can you give me an example of why this is valuable? Why, particularly with the long-term verification of the power sensors?
Well, I think that this data kind of tells the whole story, because if you're a user who wants to measure the output power of an RF generator, as an example, you can rely on the fact that these sensors are going to consistently produce good results and highly accurate results well within their published specifications. And the variance that you'll see in these measurements is very, very low, as you can see. It's essentially the best we've ever been able to do. I'm not sure, I have never seen better results in terms of variance and reproducibility of measurements that we've been able to do at high power levels, by the way. Keep in mind that when you assemble standards using just about any other method, we talked about using terminating power sensors and directional couplers, or terminating power sensors and attenuators. The error budgets associated with those systems are necessarily a lot more complex, and that translates into a lot more variance in the measurement. And you can see that as you go through the error budget process. So yeah, so that's just a couple of comments on the long-term capability of these sensors and kind of what we see.
Sure thing.
And maybe Jeff would like to speak to this, but there's some interesting play here, because unlike a calorimetric system, these sensors measure on the order of seconds, fractions of a second, really.
Right.
And so maybe, I don't know if Jeff, you would like to talk about how that was kind of interesting in the calorimetric system buildup when we were thinking about this problem.
I guess the biggest thing to look at is it's really not practical to use a calorimeter outside of this type of application, just because how long it takes to make an accurate power measurement. Like, sensors are fast, they're compact, they're small. Calorimeters have whole rooms dedicated to them. So the sensors, and like Jacob said, most of what we're seeing here in variability comes from the calorimeter itself. So when you take that sensor and you use it somewhere else, that calibration transfers really well, and the variability of the sensor and repeatability of the sensor is very, very good at that point. And I think the other thing that I wanted to point out is a lot of our sensors we're already at this level. We didn't have to make very significant hardware changes to our current pulse sensors for them to be able to hold this variability. The problem that we were having, or I don't even know if you could call it a problem, but the improvements that we made were in the calibration standards themselves. And because, like Tim said, because we have this calibration standard, everything that we make can be improved upon when calibrated with this calorimeter.
Yeah, that's just one more point to your discussion there, Jeff. It's a great time to be designing test instruments from the standpoint that some of the technology that's available, and even all the way from the RF part of that system all the way through to the analog parts of the system, to the analog to digital converters, and all the way through to where the measurements make their way into the user's hands. There's just a lot of great material out there, a lot of great components and technology that can be used in these sensors, and we use a ton of it, in the development of these sensors, as Jeff mentioned.
I think these are all great points, and I think it's been a really good discussion today. We're starting to run low on time, so I want to begin to wrap things up, but I would like to do so with some questions from the audience. And I think probably a good way to transition into that would be, we did have an audience question around what we were just discussing, as far as what does this long-term verification mean as far as potentially tracking sensor drift over time. So if Tim, do you have any comments on that?
Jacob, I'll let you take that one,
Okay,
because
yeah.
it speaks to the graph that you just were talking about. So
it shows, it's because we know the long-term reproducibility of the calorimetric system is about 0.08%. It means any variation that's above 0.08% is drift that we could detect. That is something we could confidently detect in the system. I mean, as long as our reproducibility holds up as it has, again, for 6 months now, we'll be able to take that and be able to, fractions of a percent level, basically, understand what a sensor is doing and how a sensor is drifting. That's what this graph is showing, is basically within the specifications of the calorimetric system, we can't measure any drift in these sensors. And not because our calibration isn't good enough, isn't inaccurate. It's also true with the legacy calorimetric system, but that's because that one has a 0.32% repeatability. This one has a 0.08% reproducibility, repeatability, and it's something we could start detecting. We haven't actually seen that yet in our sensors, but as we go along and we learn more about this, we will see what the long-term drift looks like at that level.
Thank you. I think it's some great stuff. One thing I want to do as we continue to work through these questions is I just want to share a slide, some key takeaways for the audience concerning calorimetry. And I just want this up for your review as we take a look at what else we've got here. So I know one of the questions is, what is the difference in uncertainty between the calorimetry and the terminating sensor methods?
Go ahead, Jacob.
Yeah, I'll field this one again. So again, any terminating power sensor measurement has to eventually go back through calorimetry for its measurement. So inherently, any repeatability, reproducibility errors in the calorimetric system will then propagate down to the terminating power itself. And what this means is you're going to have always a more accurate measurement with calorimetry. And now why is because you have to think about all the standards that are coming after it. And the simplest way to make a terminating power sensor measurement and calibrate it would possibly just be to stick it on the calorimetric system itself. However, you have to remember that that system was not designed to be together. Whatever coupler you put there, whatever terminating power sensor you put there, they were not built for each other, whereas the bird sensors are. But you could give, and that terminating power sensor is also very dependent on environment. The most accurate ones are. They're thermal devices themselves, so they will fluctuate as your environment fluctuates. So that's something to consider. So uncertainty budget, best case scenario, if you try to calibrate a terminating power sensor with the calorimetric system, we probably estimated around 0.6, 0.7, 0.8%, somewhere in that range. There's other methods to calibrate power sensors, but they will have likely more uncertainty than that even. Well, they will have more uncertainty than inherently because they have to go back through calorimetry.
Right, and that's just the terminating power sensor itself, right? I mean, that's the terminating power. So if you calibrate that on the calorimeter,
yes, then that's just the terminating power sensor itself. Right. Yeah.
So one of the resources, Steve, to answer your question, just to expand on that a little bit, one of the resources that's available, if you really want to learn more about terminating power sensors and how the error budgets work, Hewlett-Packard many years ago published application note 64, and I'm not sure which version is out there now, but there's a lot of information in that on how to use terminating power sensors to make measurements. But again, when they're used in combination to make high power measurements in combination with an attenuator or directional coupler, that the attenuation factor of the main transmission line to the coupler sidearm is critical, as well as there's a very significant mismatch uncertainty that's associated with the mismatch that exists between the coupler sidearm and the input to the terminating power sensor. So those are very significant sources of uncertainty in terms of the overall error budget for that instrument, for that approach.
Thank you, Tim. Jeff, you're being awfully quiet over there. I don't want to leave you lonely. Do you have any other points you want to make to that? I don't want to leave you.
Just to summarize, a calorimeter measurement, or the repeatability of the calorimeter is almost 10 times better than the terminating power sensor. I'll just add that summary. Do the quick math for you guys.
Sure thing. And I do have another question here. I thought it was interesting, especially because we were talking a lot about timing as far as the time to take these different measurements. Now, Jeff, you've done a lot of work with calibrating these different sensors. How long does it usually take to calibrate one of these sensors on the calorimeter?
It really depends on how many frequency points you want to calibrate at. But in general, for our pulse sensors, the 0.5% sensors that we're making, it takes about 24 hours to calibrate one sensor on a calorimeter. And that's because of what we've been talking about, where it takes a lot of time for the calorimeter to stabilize, and And we wait that long because we want the best accuracy that we can get.
Thank you, Jeff.
Thank you.
Thanks,
Okay.
guys.